Before we continue in section 4.2, do you have homework questions at all?
I was thinking on the one we did last week about the chain or
The chain one?
Yeah. Except mine is do it by 2.
Yours increases by 2?
Yeah, like it's the track 1 mile long that is family fixed on each end. On a Tuesday, so the track is driven by A equal to B and the bar buckled in the middle.
So yours has a 1 mile long track,
Yeah.
and it increases by 2 feet?
Yep.
And then we're trying to find this height that it buckles in the middle. Okay. So what we do is we take and write this as feet. 5,280 feet are in 1 mile, and that means when you increase that by 2, you have 5,281 feet. Now half of that is on one side of the buckle and half is on the other. So we'll go ahead and divide that by 2. So half of the miles on this side, that's 2,640 feet. And half of the mile and 2 feet is on this side, so that's 2,641 feet. So everybody has 2,640 on the bottom of theirs, but then you have 2,600 plus 2,640 plus half of however much it buckled. So in your case, it's half of 2 or 1. Okay, so we use the Pythagorean theorem. This is the C because it's opposite the right angle there. So x squared plus 2640 squared equals 2641 squared. And then square this 2641. Once you've squared both sides of the equation, or both of those numbers, you can subtract the 600 from both sides. So there's 5,281, and then we'll take the square root of both sides. So did you try 72.67? If that doesn't work, see me after class. Okay. Is there anybody else who's on this one? We can go over it after class as well. Does anybody have other questions? Yes.
4.2, I don't know. I guess this is something we covered in class. I just didn't know.
Let's see if we got that far.
07, question of where to place the guards.
Oh, okay.
The perfect combination of all of them. So it's finicky.
We're still working on it, but we'll check and see if we got that hard.
Something in common.
Number 7 right here?
Yeah.
Okay, so I better make it a little smaller so it all shows up on the screen. So it looks like we have 2 options for each figure. So in this option, the guides can see all the way 360 degrees over to here, but it looks like this guard, I wonder if this is a straight line. I think it probably is. If it is, they can see into here. So we just send out straight lines. So this guard on the left is not able to see this little corner, and it's not able to see this. But it looks like this guard can see into this corner. So this guard is unable to see in this little corner, and this guard's unable to see in that little corner. So it depends if they mean for this guard to be able to see in this corner. Is this a straight line here? I don't have a ruler to lay on the screen to see. Okay. So if you pick this one and it didn't work, it's because the guard right here is unable to see in that little tiny corner.
You have to pick multiple ones too.
Oh, there could be more than one?
Or at least, I guess, no, for each of the shapes. So I guess
For each shape you can pick
there's
two
one.
if you want.
No, for each shape.
For each shape there's one. Oh, I'll pick it and then we'll see. How's that? Okay, so I'll pick that one. And now this one, this guard's not going to be able to see down here, so we'll forget that one. But this guard can see 360 degrees, so it can see in this big chunk and in this chunk, and this guard can see down here. So we'll pick this one. And then on this one, this guard can see in this little piece and this piece. This left-hand guard is not able to see right up in there, but the left-hand guard can see all the way around in here, and the left-hand guard is not able to see down in this corner right here either. The right-hand guard, on the other hand, is not able to see up here at all. And this, well, maybe, let's see. No, this right-hand guard can't see up in here at all, and since the left-hand guard couldn't see up here, we're going to discard this as an option. So this one's no good. Let's pick this one. So this guard can see all around here. This guard can see, oh, yep, this is the one. This guard can see all around. So let's submit that and we'll see how that works. Do you all have the same, I got it wrong? Does it tell you which ones are wrong? No. Okay, then I'm going to say that this guard cannot see in this little tiny corner, besides not seeing up there. Pardon?
Yeah.
This one, right? Not that one?
Oh, it's the second one. Oh my God.
This
And
one?
then it's the fourth one, and then it's the last one. So it's according to mine.
Okay. Yeah, so that was it. This guard is not able to see in this little corner. Evidently, that's not quite a straight line to get in that whole area over there. Okay. Any other questions? Okay. I also wanted to show you the grade calculator. So if you have been watching videos or coming to class, then in class I try and help you see how to prepare for the quizzes. But I think some of you maybe didn't understand that you do need to probably practice things that take work or that you have to prove. So those kinds of things need practice. So if you didn't do well in your first quiz, you can turn that around by just keeping that in mind, that proofs have to be practiced regularly, and so do other things that you have to show. And I always try to tell you that during a lecture so that you know to prepare. But at any rate, if you're wondering, well, how did your first quiz affect you, you can go to this grade calculator on D2L content and open it on a computer where you have a spreadsheet available. So I have some sample students, but you can fill in your own grades here. So if you didn't do as well as you'd like on the first quiz, you can say, well, what do I have to get on the other quizzes to still get a C in the class? Or what do I have to get on the other quizzes to get a B? Remember, I'll be dropping your 3 worst Wiley Plus and your 3 worst class activities, so hopefully you can do pretty well in those 2 categories. So this student would get a C yet, even though they didn't do so well on the first quiz if they did well on their homework. That kind of has a big effect, though. Look, if I just drop this down to 85 on these 2, well, they still get a C. That's all right, I guess. So you can fool around however which way you want. I mean, if you want to say, well, could I still get an A? Then you can go in that direction. If you wonder, how low can I go and get a C? You can go in that direction, but I don't advise it. Don't try and just get by. Does anybody have any questions on the grade calculator? Yeah.
Are we going to get our quizzes back?
No. Quizzes are not returned, but you're welcome to stop by my office and see it. Okay, and also online students, if you aren't able to stop by my office, if you email me, I'll tell you, well, you missed the Pythagorean theorem, or you missed the proof of irrational numbers, or what have you. Okay. Any other questions? Okay. We're looking at the art gallery theorem in 4.2, so we're continuing in 4.2. The life lesson in 4.2 is that often in life, hard questions have answers that are made up of many easy pieces, and we'll see that as we look at how the art gallery proof is worked out. So let's just review the art gallery proof, but let's not write it out again because it's quite long. So we're looking at polygonal closed curves. Those are curves that were connected with that were formed by connecting straight lines end to end until they connected on themselves again. And the art gallery theorem said, suppose we have a polygonal closed curve in the plane with v vertices, then there are v over 3 vertices from which it is possible to view every point in the interior of the curve. If v over 3 is not an integer, then the largest number of vertices we need is the biggest integer less than v over 3. We are able to see every point inside from less than or equal to v over 3 vertices. So let's go ahead and look up the smallest easy piece of that. Okay, so we're making polygonal closed curves. What would be the smallest polygonal closed curve, or the simplest polygonal closed curve you could make?
Square.
Triangle? Okay. So if the simplest polygonal closed curve is a triangle, where would you put a security guard? Remember, we're restricting ourselves to the vertices. So which one of the vertices would you have to put the security guard at? Top one? Okay. Anybody say a different one? Yes. Any. So if you put the guard at any corner, the guard can see 360 degrees, or sometimes I'll say cameras instead. So when I say cameras, I mean cameras that see 360 degrees around them. Okay, but the camera can see from any corner, or the guard can see from any corner the whole interior. So that only takes one guard. So what we're going to do is take our shapes and triangulate them. We're going to break them up into triangles. Now, as you break them up into triangles, make sure there's no crossed lines, and no crossed lines, and that we only have our ends of our lines we're drawing go to vertices. So we're going to triangulate. We're going to triangulate our shapes. These particular shapes are polygonal closed curves, but that takes a lot of writing, so we'll just say shapes. So let me just draw one down here. If you have one of yours yet from last class, you can use that one. And we're going to triangulate it. So we're going to break it up into triangles, so you can use the one that you made in class, or you can use this one. I'll use a different color implement here. I like purple. Purple's cheery on a gray day like this. Did anybody else think today was supposed to be kind of nice? No. Yeah, it's not. Yeah, you knew it was coming, huh? I thought it was supposed to be kind of nice today. All right, so I'm going to make a triangle there. You see, the ends of my line I drew go to the vertices. And we know we can keep doing this because as I connect two vertices, I either make a triangle or a shape that's not a triangle. Well, if I make a shape that's not a triangle, I can do the same process again. So here I'll connect two more vertices. And this time I made only triangles. So there's only triangles there. So whenever we draw to connect two vertices that were not connected before, we create two shapes. If the shape's a triangle, good, we're set. If the shape's not a triangle, then we continue on. So we're going to triangulate this, and we triangulate it in a special way. And then what we do is we put colors at each of the three vertices of one of the triangles. So we're going to use red, white, and blue because that's easy to remember. And I'll just take that first triangle I made and put red at this vertice, white here, and blue here. So you do that at yours, on yours, if it's the picture that I have or if you're using your picture from Wednesday. Now we want every triangle we make to have a red vertice, a white vertice, and a blue vertice. So you have to use a little caution after you do the first one. So, for example, when I did the first one, this line that's marked R and B goes to this other triangle. So that means this one has to be white. So I don't have more than one red or more than one blue. So once you've started your first triangle, it dictates what colors you're going to put at your other vertices. So now my last triangle has white and red already, so I put blue at the last corner. So I did this triangulation. I colored each of the corners either red, white, or blue. I didn't really color it. I just put R, W, or B. And my question is, how might the coloring of the vertices relate to the art gallery theorem? How might the coloring of the vertices relate to the art gallery theorem? So remember what the art gallery theorem was saying. The art gallery theorem was saying count the vertices. So this particular shape has 4 vertices. The vertices are where the straight lines are connecting, the corners. Thank you. It does have 5. And the art gallery theorem said that the most security guards that I need would be 5 divided by 3, which is 1 2/3, or 1.6 repeating. So the art gallery theorem said that when you divide the number of vertices by 3, if you get a number that's not an integer, that you take the integer that's the next number down. So 1 guard needed. You take the whole part of the decimal you get when you take 1 divided by 3. So the art gallery theorem says I need 1 guard needed. How might coloring this blue, white, red, blue, white, how might the coloring of the vertices relate to the art gallery theorem? Does anybody have any ideas on that?
Could be their sight lines.
Could be their sight lines. Can you elaborate on that?
If you have a guard at that first R,
First R.
they can see everything, and you can tell by the lines.
Yeah, so the guard at R can see everything. Okay, and how does the guard at R relate to the 1 guard needed? I mean, did you pick R because there was 1 R? Like why did you pick this guy instead of this guy? Because this is actually an interesting shape in that a guard at any corner can see the whole art museum.
just because that's where the lines originated from.
Oh, okay, so you were picking R because the lines were coming out from there, okay. Well, it turns out that the R is related, but I just happened to draw the lines coming out. I just happened to color that one. Like I could have put the line this way, the last line I drew that way. Anybody have any other ideas? Okay, so let's see what we have. We have 2 W's, 2 B's, and 1 R. So it is related to the R. We should put any color that we pick. Well, let's not say right away. Let's see if you can think about it while we do another one. Let's do the one that was at the very first page that we started. Let's draw this on a piece of paper. And then let's do the same thing with the triangulating and the coloring and see if we can come up with how the coloring is related to the art gallery there. Okay, so I'm going to draw this shape. So let's go ahead and triangulate that. There's more than one way to do this, and there's not a right way. So well, there is a right way in that you must have no crossed lines, and the ends have to go to the vertices only. If you use a straight edge, it makes it neater looking. And if you're like the first time I did this, I had to use a pencil because I kept messing it up. So you might want to use a pencil. So we're just connecting vertices to form triangles. Now it's tempting here to just cut off this tip here, but you can't do that because there's not a vertice right here. So don't do that. Only connect vertices to vertices. Now this piece right here is probably a triangle. It looks like it for sure in the drawing I made, but in the original shape, I'm not sure these two pieces are level. So I'm going to go ahead and put some triangles here just to be on the safe side, okay? So as long as you're connecting vertices to vertices, you're okay making sure that a side that looks like it might not lie on a straight line is made into more triangles by connecting more vertices together. So just so you connect vertices to vertices. So go ahead and label these. I'll just start with the beginning triangle I made, red, white, and blue. And once you've labeled one of your triangles, it's going to tell you what you have left for choices in the next triangle touching. So if I label this red, white, and blue, then since I have red and blue here, this corner has to be white. Now I have blue and white, so this corner has to be red. Now I have red and white, so this corner has to be blue. Now I have red and blue, so this corner has to be white. Here I have blue and white, so this corner has to be red. Now I have red and white, so this corner has to be blue. Let's count the vertices. and see what the art gallery theorem says for the number of guards needed. And then let's go ahead and count the colors that we have at the vertices. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 vertices. So 9 divided by 3 means that we have at most 3 guards. And now for reds, I have 1, 2, 3 reds. For blues, I have 1, 2, 3 blues. For whites, I have 3 whites. So what does the art gallery theorem have to do with the way we've triangulated and colored this polynomial closed curve? We'll take one color at a time. Okay, so front row, everybody in the front row, look at the blue and determine if you put cameras at blue, would you see everything? Second row, look at the white. Third row, look at the red. Okay? So blue in front, white in the middle, red in the back row. See if your color, if you put cameras where your color is, could you see the whole gallery? Okay, ask your neighbor if you have someone next to you. What did you decide, Red? Yes. Wait, was Red in the back?
Yeah.
And you said yes? Okay. Red, so if we put our cameras here, then Red can see all of this triangle. Because remember, if you're on the vertice of a triangle, you can see that whole triangle. You can see everything inside the triangle because you can see 360 degrees. So you see that whole triangle. And you're on this triangle also. So you see this whole triangle. Red sees this whole triangle. This red sees these 3 triangles, actually. This red guard sees these 2. Okay. So we could put our cameras just on the red corners. How about who had blue? Front row? Okay, what did you decide?
Mm-hmm.
Yeah. So if you put your cameras on where the blue is, just put a blue there. Do I have blue? Oh, I circled blue instead of red before. Okay, blue is supposed to be this one. Okay, so I'll look more carefully now. So blue, this guard can see all of this triangle. You can actually see a little more. But blue can also see all of this triangle, and this triangle. And this blue guard can see all of these 3 triangles. All right, what did the white guards decide? Who's got that? The middle row? What did you decide? Can the white guards see the whole thing? Yeah. Okay, good. Okay, so can anybody tell then, how might the coloring of the vertices relate to the art gallery theorem? Yes.
It helps to reinforce why that equating the V over 3 formula is actually useful, or that in the case that it's universal. It's not like a proof, right?
We haven't got to a formal
But
proof.
it's an example of how you use it. I don't know.
Yeah, it's an example of why it works, isn't it? It's an example of why it works because it breaks it down into triangles, and if you're on any vertice of a triangle, you can see the whole triangle. So if we just pick one color camera, there's one color camera on each of those triangles. So there's a blue camera on each triangle, or a white, or a red. So if you put your cameras on just the blue vertices, or if you put your cameras on just the white vertices, or if you put your cameras on just the red vertices, you will see the whole area. And since our line's only connected to vertices, that means we're dividing up the vertices in 3 colors. Okay, so that's where we get the V over 3, because you're taking all the vertices there are and you're dividing them among 3 colors. Well, you're not going to get more than V divided by 3 vertices then. So up here, since we had 2 white vertices, 2 blue vertices, and 1 red vertice, we'd choose to put the camera on the red vertice, because the red vertice then was the least number, so that's where we would put the camera. And then it turned out, oh, you know what, it does have what you were saying then, because it's radiating from there. So all the triangles are touching that angle, so that vertice can see into all of the triangles. So once you triangulate your polygonal closed curve, you just have to label it correctly and then pick. See how many vertices come in each color and pick the least one. Here we could pick the least one. Here they were all the same, so it didn't matter which. Okay, so I'll just say put cameras at all of the blue ones. But you could easily, just as well said, put cameras at all the red ones or put cameras at all the white ones, and it would have been just equally valid. Now this is the kind of thing I'd like you to be able to do on a quiz, and so I brought you some polygonal closed curves to practice on. There's not just one way to do this, so if yours comes out different than the person's next to you or than mine, that doesn't mean it's wrong. What you want to make sure is that all of your triangles have red, white, and blue. You don't want to have a triangle with 2 blues or a triangle with 2 whites. You also want to make sure that there's no crossed lines and that your ends go to the vertices only. Okay, so I'd like you to triangulate these. Color them with, you don't have to actually use colors, you can use red, white, and blue. And then count the vertices. Count the vertices, how many are each color. How many are each color, and then where to put the cameras. So place the cameras with a circle around the R, B, or W, whichever you decide. Remember, your circles should all be on R's, or all be on B's, or all be on W's if you did everything correctly. So this is the kind of thing I'd have you do on a quiz. So I brought some for you. Online students, this is on D12 content. And you might want to practice this before the quiz and download some more of these as well. Do you do that? What does that mean? Do that fancy coloring?
No, I just kind of have one.
Because there's a name for that. So I'll come around and see how you're doing, but please raise your hand if you're stuck. I'll be glad to help you out. Remember, no crossed lines and only connecting at corners. There's more than one way to do these.
I'd be curious to see when the cameras are on. 2 minutes. Well, I don't know. I'm really interested.
Since it's not clear that this is a horizontal line, in fact, I think it might be a little tippy at places, then you should connect this one to here, like I did up there actually, yeah. If you made the shape yourself and you were positive it was straight, then you wouldn't have to worry. Wait, let's see. Well, see that, I think you have to actually connect this over here, because you're not sure that the projects straight in there. Okay, that way then you won't have DB. I don't know, let's see, then what color will this be? So you have red, white, I think you gotta do your coloring over.
Probably.
Draw that in. Okay. Looks like that's working out, doesn't it? The thing is, like, you didn't have a triangle, you're like, wait a minute, there's two whites here. How many cameras do you end up from this one? 2, 4?
Yeah.
Yeah, I guess that one. See, how's your red, white, and blue one?
Once I get the hang of it, yeah. Because when I first saw it there, I'm confused, and now I'm just like, what's in my head? I'm gonna do it.
Okay. Are you red, white, and blue? No. Stop. I'm not over here. Do they feel like we're getting the same, all a different color? Would you want to see? I'll try to see the same. So you have red and blue. Oh, this one, you started this one, red, white, and blue. So that this is white and this is red, and this one is blue. And then this is blue and this is red, and that one. So, and then this is blue and this is blue and white. Ah, it's not working with it. Let's see, we start here. Blue. So that means that one is blue. Oh, we should have gone here next, because we have two sides. So then we should go there next, and then over here. So what would that one?
Or no.
And these right there. So it's really easy. I directed you the wrong way. Okay, so you pick this one to start, and I'll hold you this one next. And now you have this line, so that holds you this one next. And then you have this line, so that holds you this one next. Perfect. So I'll try and catch up. A lot of you are ahead of me. So if you have a starting point, you just color red, white, and blue. But then do the triangle that connects to it so that you don't get off a color. I've had to erase a lot before I figured that out. So this triangle has a blue and white here, which is the side for this triangle, and that tells me now this has to be red. So always the next triangle to work with is one that you've labeled a side for. So I've labeled this side on this triangle, so this one now has to be white. Now I have this side done, so this has to be red. I have this side done on this triangle, so this has to be blue. I have white and blue, so this has to be red. So whatever triangle you have one side done for, after you do the first triangle, that's the triangle to do next. Is anybody stuck? I can come around and take a look at that. Okay, so I pick a color, red, white, and blue, on one triangle, and that tells me on the triangle that's connected what color to do. So we'll label one triangle, and that gives you a side for another triangle, and when you have a side for another triangle, that's the one to work on next. So there's more than one ways to do this, more than one way to do this. To do the triangulating and where you place your colors, but you should always have all three colors on every single triangle if you've done it correctly. So you can count how many you have on each then. So this one, how many vertices did this one have? Did anybody get this one done? 11 vertices. So the arc gallery theorem says you need 11 divided by 3 or 3.6. So we need 3. 3 at the most. And we're going to verify that by looking at how many red corners, how many white corners, and how many blue corners there are. So on mine, I have 1, 2, 3, 4 red. Blue, I have 3. And white, I have 4. So that's my 11 vertices. So I picked the smaller number, 3. I'm going to pick 3 blue, and I circle those, and that's where the camera goes. So cameras placed at those 3 places can see into all the triangles where that vertex is attached. And so we're covering all the triangles that way. This one, 1, 2, 3, 4, 5, 6, 7 vertices. So the arc gallery theorem says 7 divided by 3, which is 2 1/3. So 2 at most. So let's verify that by looking. We have, in mine we have 3 blue, 3 white, and 1 red. So I'm going to actually put one camera right there, okay? And then I put a circle to show that. So this is the kind of drawing that I'll expect you to see on your, quiz eventually. How many vertices does this one have? 9 vertices. So I should be able to have 3 at most. 1, 2, 3, 4 red, 3 white, 2 blue. So in this problem, I could use 2 cameras the way I did it. Did anybody find a way where they made theirs where you ended up having to have the 3 cameras on that one? Yeah? Okay.
I could use any.
Because you had like 3, 3, and 3? Yeah.
Mm-hmm.
So depending on how you did that, that might very well happen. So I know that's a possibility, and on a quiz I'll be checking to see. Do you have red, white, and blue on each triangle? And that's how I'll check, okay. This one I'm just going to put this up that I did earlier. Okay. So I wanted to show you the person who proved this the way we're working with it, and that person is Steve Fisk. So this was this art gallery question was proposed in 1973, and it was proven shortly thereafter by someone Chevaltau. But here's what Professor Fisk says. Here's the quick story. My wife and I were traveling across Asia during 1975 to 1976, and during our 1-month stay in Iran, I visited the math library at the University of Tehran. I read Cheval's article, or rather I looked at it, for the proof seemed so complex that I didn't want to read it. I did like the result though. A few weeks later, we were traveling on a bus between Herat and Kandahar in Afghanistan. It was hot, dusty, and noisy with squawking chickens on the roof. I was thinking about it. Well, I was probably dozing off actually, and I thought of the proof. So that is actually how mathematicians work. I was going to we were interviewing a candidate to work here at UW Green Bay for a math lecturer position, and Tian Hu, a professor who worked here with me, and I were taking this candidate out to lunch, and she was a very quiet candidate, and I was quiet, and we're like struggling to make conversation, and I'm looking at Tian to chip in his little bit here and carry the conversation, and he's like staring off in the window. I'm like, what are you doing? So we struggled along, this poor candidate and I, and finally after, when I could talk to Tian alone, I'm like, what were you thinking of? And he's like, oh, well, I was just thinking about a proof I was doing. Well, Fisk's proof is very beautiful, very elegant. In fact, his proof was so short and elegant, it was chosen for inclusion in Proofs by the Book. This is from Wikipedia. So he says, first the polygon is triangulated, which is what we did and what you see here in the picture, without adding extra vertices. It is knowing that the vertices of the resulting triangulation graph may be three-colored. Clearly, under a three-coloring, every triangle must have all three colors. The vertices with any one color form a valid guard set because each triangle of the polygon is guarded by its vertices with that color. Since the three colors partition the end vertices of a polygon, the color with the fewest vertices defines a valid guard set, at most n divided by 3 guards. So that is a very beautiful, elegant proof. Well, here's where we'll stop then, and have a wonderful spring break. Take a picture of this. This is what you upload into detailed content. So I'm sorry if you already put it away. Take a picture of that little sheet, all triangulated, and load it to your Dropbox Sunday night.
Okay.
I'll see you.
So you're not sure of everything. I put the Pythagorean picture in for this. I thought it was an art gallery. I don't know.